Okay, well, for our next talk, we're very pleased to have Klinger Logan from Kansas State, who will tell us about connections between special values of L functions and scattering amplitudes.
Well, thank you so much for having me, and thank you to the organizers for putting this together and bringing such a great group together. The first two talks were truly amazing. So most of what I'll be talking about today is in collaboration with Ksenia Fedosova and Stephen D. Miller and Danylo Radchenko. It was working. Did I go the wrong direction? It's making a noise like it wants to work? Of course.
Oh, I have one. What's that?
I have one too. Let's see here. Is it not? It was just, am I?
I'm gonna try yours.
Try this. Okay, yeah, sure.
There's a thing over here. So
Sure.
I'm sorry.
No, you're fine.
Like for the unselectable.
Sensitive, no worries. What? What? I can just stand here too. Oh, maybe if I want to, oh, maybe I have to click on the slide, because maybe this is the. You're good. Let me just, there we go. Now we're good. Okay, cool. Success. Okay, so I'll just note, so Kansas is the historical home of many Native nations, including the Kaw, Osage, and Pawnee. And so as a land grant institution, Kansas State, where much of this work has taken place, it was and still is on land stolen from the institution. So I just wanted to acknowledge that fact before diving in. So what I want to talk about today, hopefully I didn't write this too small because I know this room is quite big. So let me know if there's anything that you can't see, but is two major applications of differential equations involving automorphic forms. And so these are like a Poisson type equation, so an eigenvalue equation, but instead of being homogeneous set equal to 0, set equal to some data on the right side. So here S might be some sort of distribution or a function of moderate growth. G here we can think of as a reductive group or some semi-simple Lie group of some variety depending on the context. So I'll kind of spell out the details of what equations we're talking about in each context. But we have these two major applications that I'm going to talk about. So one is relating to is solutions in the form of these eigenvalues might tell us about zeros of L functions. And the other is the eigenfunction solutions to equations of a similar form can tell us about scattering amplitudes for certain particles. So I'll walk through each of these two kind of applications, but I think it fits. This was the best I could do to fit a theme of arithmetic quantum field theory. It was like, well, I don't do arithmetic and I don't do quantum field theory, but here we go, you know. In both the settings that we'll be talking about, both the number theoretic setting and the physics setting, kind of the most basic classical group that we can talk about is SL2. And so here is, I mean, as many of us are familiar, in the number theoretic setting, we want G to be some sort of reductive group. And in the physics setting that I'll be talking about is the type 2B supersymmetric string theory, which kind of the size, the group G will depend on the amount of toroidal compactifications you do. So in the full thing, we'll be looking at E8, the exceptional group Lie group E8, you can consider by doing, let's see, I guess, what is it, more toroidal compactifications? We're going to be taking different subgroups of, or I guess less toroidal compactifications, we'll be looking different subgroups of the exceptional group Lie8 by just removing an element, one of the nodes of the Dinkin diagram, giving us this characterization in that most basic case, we're looking at SL2. So that's just kind of the context for why I'm looking at this particular group. But just to say that many of the things we'll be talking about have at least motivation to be thinking about G as something a little more complicated than SL2. Okay. So just as a refresher, for G being SL2, unlike Charlotte's wonderful talk about the p-adics, I'm just going to be looking at the Archimedean case. So, no TV shows about this, I suppose. But in the Archimedean case, at least, so we have, we can represent this space as, the fundamental domain being this this green strip here, and our invariant Laplace-Beltrami operator on this space is like the Euclidean Laplacian, but with its extra y squared. And here we have two types of eigenfunctions, cut forms whose Fourier coefficient is 0, and then these non-holomorphic Eisenstein series parameterized by cosets over parabolics. Okay, so so the basic idea as a broad summary is, if kind of depending on what S might look like, one way that I might solve a differential equation in this form where delta is some Laplace-Beltrami operator is by writing a spectral expansion for the right-hand side. And so in the SL2 case here, as long as S is in, you can think of X being in L2. Anytime you see an H, you could really kind of, L2 is a nice example of this, but more generally, this is any global automorphic Sobolev space. And so S could be a distribution in that sense. So in that sense, we can write a nice convergent spectral expansion for S in terms of an orthonormal basis of cut forms, and then some continuous spectra. And so to solve such a differential equation, I can think of kind of writing that expansion out for S and then dividing by these eigenvalues, these spectral values for both S and F. And here we can, and this solution will converge nicely for real part W greater than 1/2, but we can also meromorphically continue the solution in this parameter W, which is that same parameter that matches up with parameterizes my eigenvalues. Okay. So this is like kind of the general formula I want to think about for solving a differential equation like this. And where I ran into this type of solution for the first time was in a particular application that works with zeros of L functions. And so as a refresher, of course, the Riemann hypothesis says that we have, we want to show that all of the non-trivial zeros of the Riemann zeta function lie on this critical line, real part S equals 1/2. And Hilbert and Poya suggested that one way to attempt to prove this conjecture is that we could find a self-adjoint operator so that all of the zeros of zeta appear as the spectral parameters lambda, so as W values here, for that operator. Okay, and so by the spectral theorem for self-adjoint operators on Hilbert spaces, that would mean that all of these lambda W's are real. And if we parameterize lambda in this way as W times W minus 1 or 1 minus W, then that would mean that the zeros of zeta are either on the critical line or maybe on the real axis. Okay, so this is an idea of how we might approach this problem. But of course, the question is, okay, that's great, but where do we find such a candidate operator? So one place to look is a story from 1977. So Haas was doing his master's thesis under Neuenhofer and asked him to find these values lambda W for delta, so eigenvalues for the self-adjoint Laplace-Beltrami operator. And so we found this list of W values, and Neuenhofer, his advisor, presumably sent this list to a number of people. One of the places he sent it was to Audrey Terrace at UCSD. He also sent it, and Stark and Hejhal were there as well. And they noted a bunch of zeros of data, and this is the L function attached to so a Dirichlet L function attached to the quadratic character for Q adjoin -√3. So we found these values on the list, and so Hejhal wrote a letter back to Neuenhofer and asked him how these computations were run, and Neuenhofer said, gave him some information back, and Hejhal redid the computations and noticed that all of these special L values were missing from the list. Now, all the other values, eigenvalues for this Laplacian were there, but the zeros of zeta and L were missing. And what Hejhal had noticed was that what Haas actually computed was, instead of computing genuine eigenvalues, he'd made some sort of, what was it called? Allowed for some sort of non-smoothness at the corners of the fundamental domain, and had actually solved an inhomogeneous equation set equal to a Dirac delta here. So you can think of this as like your usual Dirac delta supported at 0, but it's supported here at the corner of the fundamental domain, and then it's just made automorphic by kind of winding it up over the cosets here. So almost homogeneous, but that means that these things aren't genuine eigenvalues, right? And so we don't get something like the Poisson-Hilbert conjecture exactly. So the question becomes, well, how do I take this inhomogeneous equation? Is there a way to take this inhomogeneous thing and turn it into something homogeneous with a genuine self-adjoint operator? And so after Hejhal wrote his findings in 81, Colin de Verdiere wrote a series of papers in 82 and 83 with some ideas of how we might work around this obstacle. And he made some observations. So one of his first observations is that if I have some sort of inhomogeneous differential equation, and I also satisfy some sort of boundary condition, I can set that thing is equivalent to a homogeneous equation, where this new operator that we're making is, we basically take some sort of restriction of the domain, and then the Friedrichs extension, which is one of the canonical extensions in the von Neumann listing of the self-adjoint extension. So this thing is going to be self-adjoint here. And so, so at least in one particular instance, there's a way of taking these particular inhomogeneous equation set equal to a distribution and making it homogeneous with a self-adjoint operator. Now, what I believe he wrote this result for was where this distribution is not the delta we have here, but this operator that says take f and evaluate at the constant term at height a. So it's not the same thing as our automorphic distribution. This Friedrichs extension operator is related to the Lax-Phillips operator that were studied in their 1976 paper. So it has some really interesting subtleties going on with the spectrum of this operator. But yeah, so then the question was, okay, that Colin de Verdiere wanted to address was, okay, can we do a similar construction for something like this Dirac delta that we have from this particular setup? And he realized that one of the main contingencies for this equivalence, or this biconditional, is that this Dirac delta, which I forgot to change, this Dirac delta that we have is not actually in the correct Sobolev space, so it doesn't have quite enough convergence in order for this conditional to be true. So his solution to his potential solution in order to get around this obstacle was to actually project my automorphic Dirac delta to the non-cuspidal spectrum. And so when you do this, we get the right amount of convergence and can basically form this kind of quasi lax Phillips operator that we have here. But if it's, instead of being associated with A to A, we can kind of analyze what's happening with this automorphic delta, or the projection of that automorphic delta. And what more recently Bombieri and Garrett found was that the spectrum of this new operator, so the restriction of delta, so we're going to restrict delta to the kernel of theta, which is this projection, and we're going to take the Friedrichs extension of this thing. So these eigenvalues are completely contained in the online zeros of zeta and this L function. Now, of course, what we want is the inequality to go the other way. But equals works. We don't have equals, is the other thing that they realized. And the reason why we know we don't have that these two things are equal is by examining the spectrum of this operator and examining how those eigenvalues are spread out. So specifically, when we look at the spread of these eigenvalues for this operator, they conflict with what pair correlation says the spread of the zeros of the zeta function should be on the critical line, okay? And so we have, let's see, and so this conflict means that at very most, 94% of the zeros of zeta could be achieved within this spectrum. Now, there's not really any good motivation to think that we only have 94% of them and not maybe all of them. And in fact, there's not even any proof that this spectrum is not empty, that once we've done this restriction and the extension, that we didn't just get rid of the entire spectrum of this operator. Okay, and actually computing this is a non-trivial thing. So there are some positive things we could say in this direction, and there's still a lot of questions as we're kind of alluding to here. But before I say anything kind of more positive in this direction, you might ask, how could we even prove such a thing? Especially, I did get once, how can you prove anything about the spectrum of this operator if you don't even know that there's anything in it? And I said, but we're mathematicians. Isn't that what we do? So anyway, how can we prove such a thing? And we can prove such a thing by using this sort of spectral solution for my differential equation. So remember, we have this differential equation. Here we're setting equal to that projected distribution instead of the automorphic Dirac delta. So I write out, since this delta is in some Sokolov space, I can write a convergent spectral expansion for it. And then, which will just involve some constant terms and some integrals against Eisenstein series. And I divide by the spectral values. So this kind of expression is what's allowing me to analyze these spectral values. And this expression converges for real part W greater than a half. We can meromorphically continue in W this expansion by doing a regularization argument where I basically add and subtract some version of this evaluated at W, and I can evaluate this new integral. So when I add and subtract that thing and I evaluate the extra piece that's sort of come out, I end up with this extra term in my as an identity here. So I get that f of W is something like this thing where I subtracted the EWs, and then this is the piece that I added. So this gives me a functional equation where the solution is not exactly equal to W to 1 minus W. It's not over our usual functional equation, but we have an extra term here. So an interesting fact about this extra term in this meromorphic continuation is if we actually didn't have this extra term, this would serve, you would be able to prove some asymptotic version of the Riemann hypothesis without this thing. But it is importantly there from this meromorphic continuation. Okay, so writing out the spectral solution this way allows us to kind of analyze what's happening with these spectral values. And some sort of positive thing that we can say about this is even not hinging on the fact that we don't know that the spectrum is not empty. We do have some sort of spacing results that we can say about zeta and this L function. And now they're kind of hard to parse, but they basically tell us particular conditions we can satisfy to guarantee we have greater than average or half average spacing between two zeros either on or off the line. Okay, so this story is sort of how I really came into to kind of work with differential equations involving automorphic forms of this type. And of course, there's many different directions we could take work in this area. So of course, we could try to get spacing results for other L functions. There's similar constructions you could do with other self-adjoint L functions based on this kind of setup. And then of course, there's many questions still remaining about the spectrum of this operator and whether or not it actually contains anything. Okay. So that story sort of motivates how I started thinking about the connection between these eigenvalues and these eigenvalues, or how I started thinking about automorphic differential equations and eigensolutions. But the other application that I want to talk about is maybe more relevant for this purpose, and it relates to computing scattering amplitudes. So, as a setup for this problem, we're going to think of quantum field theory does a really good job of modeling what's happening with different particle interactions, but it doesn't really account for gravitational forces. And so in order to model what's happening for gravitational forces, we can think of representing these particles by strings, either closed or open. And in our case, we're going to think about a closed string theory. In order to test test each of these theories, we're going to run certain computations. And so one of the computations we want to try to compute is the scattering amplitude. So we have these particles that move through space, and they take on different configurations as they interact with each other. And we're going to assign a probability to each initial and resulting state. When I do so, I can represent this thing a bunch of different ways. I have both an analytic piece and a non-analytic piece. And I'm going to think of the analytic piece. So this thing is analytic in a few different variables. When I'm looking at these strings, one of the things I want to, I now, since I'm not talking about particles, one of the quantities that I'm dependent on is basically the size of the string or the string scale. Another thing that I'm dependent on is this thing called string coupling. So the strength of the string-to-string interactions. So I have a few different variables kind of floating around in the geometry here. And so I can make this thing analytic in either the string length or something akin to this string coupling. So we're going to make it analytic in the string length, which is very small little alpha here, which each of these little sigmas, so they depend on the Mandelstam invariance, S, T, and U of momentum and energy, as well as alpha, that string length. And then G here, one of the things you can think of G representing is that string coupling, and we're placing like basically scalar fields on top of some sort of Euclidean type space. And these scalar fields based on different physical constraints are going to have different dualities. And so in our case, they're going to be G is the invariant on the left due to the U duality that we impose, and they're going to be invariant with respect to the maximal compact on the right, and so on. So the coefficients are going to be coefficients in these variables here, G on this double coset space. And so here, again, our analytic expansion is analytic in alpha, and we're looking to find these coefficients in this analytic expansion to get like a higher correction term for how we expect, or how we think particles of gravity might interact under this certain theory. So our first term here is given to us by the Einstein-Hilbert constant, and the goal is to be able to find these higher order coefficients in order to get better correction terms here.
President?
Yeah.
Does that ST means two different strings, or what's the meaning of the ST?
The ST.
S and T, yeah.
STU. So ST and U are the so those are the variables. Those are the Mandel-Stam invariants of kinetic energy and motion and momentum.
So it's just the parameters of the strings.
Right.
Oh, okay.
So it's this is a function of STU as well as alpha. I didn't put an alpha up there because sigma is dependent on ST and U. Does that make sense?
Okay.
Okay. Yeah, good. Cool. Okay, and so this is actually, I should say, this is for basically two strings starting off and then two strings ending up. This is what this energy expansion is. Okay, so our goal is to solve, to find these other equations, and due to work of Green, Russo, and Vanhove, we know that some of these first few first few coefficients satisfy a few differential equations. So for instance, the 0, 0 term satisfies this homogeneous equation. The 1, 0 term satisfies a slightly different homogeneous equation. And the 0, 1 term, so the next guy, oops, oh no, that was really bad. The fourth guy on the list satisfies a slightly weirder differential equation. We'll see if that worked. It did work. The luck is with me today. Okay, so good. So again, G here, kind of as I mapped out prior, we can think of as some sort of subgroup of E8, but in this classical example, we can think of it as SL2. And these parameters will slightly change in different groups, but on SL2, this is what things look like. It's the simplest case here. So of course, these first two things are just homogeneous equations, right? So these things have to be eigenfunctions for the Laplacian. This is that Laplace-Beltrami operator we were talking about before. So these things are solutions to these differential equations. So they turn out to be Langland's Eisenstein series or non-holomorphic Eisenstein series. Associated to a maximal parabolic subgroup in general, but here at these just two parameters, so 3/2 and 5/2. And so what remains then is computing a solution to this last one, where notice we're taking the solution here, F1, to be kind of the data on the right-hand side. So we're solving this inhomogeneous equation kind of equal to some other stuff. Okay, so equal to an Eisenstein series squared. Okay, so more generally, equations of this form, so some kind of eigenvalue type equation, but set equal to some products of Eisenstein series, show up other places in physics as well. These arise as certain correlator functions in n equals 4 super Yang-Mills theory and the 1/n expansion. And they show up in the study of modular graph functions as well. And so most of what I'm going to be talking about is the case where we have these like half integer spectral values for Eisenstein series as well, or here. But there's also in the study of modular graph functions, we're usually caring about cases where A and B are integers, and Axel Kleinschmidt has done tons of great work on those particular cases. But we'll be focusing on kind of when A and B are half integers and those types of solutions, as there's this kind of broader relationship here. Okay, so generally, I might want to try to use like this spectral solution to solve this differential equation. But the problem, remember, is that I want to take this right-hand side and I want to write a spectral identity using cusp forms and integrals against Eisenstein series. But I can only do that if my right-hand side is in a particular space, right? So usually we think of it as being in L2, which we know Eisenstein series are definitely not in L2 because of this constant term. But we also, it would suffice for this thing to be in even H negative infinity, which it's not, right? And this is kind of any Sobolev space, again, due to this constant term. And so the idea, following work of Zagier, is to basically subtract a linear combination of Eisenstein series from this product. That new thing will be in L2. So basically, I'm going to take this product EA times EB will have a leading term that looks like y to the a plus b when a and b are large. So I might subtract off EA plus b to kind of get rid of that term and have everything else be small enough. So I'm going to subtract a linear combination to get rid of the growth from this constant term. And then I'm going to write the spectral expansion for that thing. And then I'll add back in the Eisenstein series and divide by my spectral parameters. And so when I do that, here's what my solution looks like. Here's the linear combination of Eisenstein series that I first subtracted to write the spectral expansion, and then I added back in. And we can see here all of the eigenvalues that we're dividing by here. And we can compute each of these spectral coefficients for like the orthonormal basis of cusp forms F. These are completed Radchenko L functions here of a cusp form against the Eisenstein series. And of course, the most complicated and again, kind of closer following Zagier's work is this completed Eisenstein series completed L function with two Eisenstein series here. So we compute using Arthur truncation and Moth-Selberg relations to get this L function. Okay, so we know what's nice about this spectral result is that it gives us the existence and uniqueness of a modular solution or an automorphic solution for a lot of different values of A and B. So specifically anything in this purple region. We can meromorphically continue really nicely from the meromorphic continuation of these L functions to the other parts of the plane in A and B. We also have a meromorphic continuation of this thing in W that I should say for the solution using a similar regularization argument. Yeah, but this gives us the existence and uniqueness in at least a lot of different cases. The one thing that happens that's a little weird is that on these dotted lines, you notice that if you go to subtract particular Eisenstein series, you end up adding in some higher growth terms based on these different values. So there's a little bit of care that we do have some existence on those dashed lines as well. Okay, so we know a solution like this exists in many different cases of A and B. But as far as running computations, given that we don't have an explicit basis of cusp forms, and these integrals of Eisenstein against Eisenstein series are not super fun to work with, computationally this doesn't give us a ton of information. You can get the constant term in the Fourier expansion from something like this, but I think that's roughly it. So what we'd like is maybe a Fourier expansion for some sort of solution here, so that we can run computations. But then I'm going to show you what it looks like, and you're going to be like, never mind, we don't want that. No, I'm just kidding. So I'll write down the rough form that we think we have here. So this is just a conjecture because what we have is that we have the solution explicitly written in many different cases, and many, and computations have been done to show that this thing converges, but there's still a lot of questions about these types of solutions. So notice this is just for A and B being the half integer pairs. The solution looks different for integer pairs, and as far as I know, aside from the spectral solution, I don't know. And maybe Axel knows more about other work outside of the integer and half integer cases. Let's see. So if we write a Fourier expansion, the basic idea is that we might have some polynomials in y and 1 over y. We have, these are constants, so square root y times a k-Bessel function depending on the eigenvalue lambda. And then everything else should be polynomials in y and 1 over y times k-Bessel functions in 1 and 0. And this is not too unexpected, given the way that the Fourier expansion of the Eisenstein series works. You can kind of parameterize it in k-Bessel functions in 1 and 0. So, in many explicit cases, this has been computed exactly. We know what all these coefficients look like. But they are a mess. And so what we'd like to be able to do is we'd like to be able to write a closed form for these particular coefficients and a closed form for this expansion for any A and B that are at least half integers. And so this is ongoing work with Ksenia Fedosova and Don Zagier. But in one particular case, which is our case of interest, I'll just put it up here so you can see, believe me, that they're not fun to generalize this. At the 3 halves case that we were kind of initially motivating. So here's my F thing. It's not too bad. That's that 0th Fourier coefficient here. But you can kind of see like I don't even know how to parameterize it off of now in my head. Okay, so these are the next 2 coefficients. Again, not too bad. But once we get into this weird little mixed sum, things are just kind of a mess. Good. Okay, and so here's my little alpha terms as well. Okay, so as I said, we'd like to be able to write a closed form for this for any half integers alpha and beta. But right now, even just looking at like where like one particular case comes from is kind of a mess, and this is even one of the simpler examples that we can compute this way. Okay, so there are a bunch of different ways that I should say that we can come to the solution, but more importantly, this there are a bunch of mathematical questions that come from just analyzing these solutions as they are. So one is, we're asking is whether a solution of this form does actually always exist, and it seems to be that there's some sort of dependence on the size of alpha and beta with relation to, A and B with relation to the eigenvalue, in which we don't have a solution of this form. And so it's kind of interesting to see what happens outside of those cases. It seems like this might depend on some sort of rank and Cohen bracket computation. And another question we don't have the answer to explicitly is whether this thing actually is, I kind of hand wave this, but is automorphic, meaning SL2Z invariant. The way we compute it, we assume that it's translation invariant to get this solution, but we don't necessarily know that it's invariant under the S operation. The last thing is, of course, can we generalize a closed form for these Fourier coefficients? And one place we can start with looking at what's happening with these closed forms is by looking at this alpha condition. These alpha coefficient here. Let's see, maybe I can. Oh wait, no, I did it in the next slide. This alpha coefficient here. And so we're actually able to write something much cleaner for this alpha coefficient, which is actually, not the nicest of all of them, but due to some physical reasons, it's expected that each of these alpha ends should be 0 in this application. And here we can see, here's how we define each of these alpha ends. It's the sum of these alpha n1 and 2, so just kind of blowing up this piece. And this piece, just to note, it corresponds to the homogeneous solution for the differential equation. So it looks something like this. And here, so these sigma 2s are these sigma divisor functions of this form, and then some sort of weird polynomial times log situation going on here. Okay, so yeah, it was conjectured by Chester, Green, Wang, and Wen that that each one of these alpha sub n's should be 0, but they clearly don't look like 0 in each one of the n1 and n2s. And so we can rearrange these terms just to make it look a little bit cleaner here, and their conjecture looks something like this. And so what you can see is this is some sort of like shifted convolution type of sum that's happening with these sigma divisor functions here, since this n1 and n2 sum to n. And so we'd like to be able to show that this shifted convolution sum, once I kind of put these other pieces, kind of extra terms on the right-hand side, it should be equal to some sigma divisor function plus some linear combination of zeta and zeta prime.
There's some physical meaning that alpha n is supposed to be 0.
That's a question for Axel. I think so, but I don't know. Is the answer yes?
Yeah.
The answer is yes. To be continued. Good. So is it because we expect it to be a lattice thing? Is that why?
It's because it's a lattice thing, and otherwise it could correspond to sort of isolated instant-on contributions, which we don't expect for this.
Perfect.
Not sure whether this helps, but there.
Very good. Okay, so we'd like to be able to prove some identity of this variety. Danylo, Radchenko, Steve Miller, and I, we wrote up a formal proof of it using double Dirichlet series, but the problem with this formal proof is that it involves evaluating the Dirichlet series outside of the region of convergence. So it's just a heuristic, really. And then you can also run computations, and you see computationally this identity seems to be true, which you should probably do before you try to prove it, I guess. And so after writing up this formal computation or formal proof and running this computation, with Ksenia Fedosova, we thought, well, okay, maybe in this one particular instance, we're not seeing what's going on. Let's see if we can try to prove the heuristic for other differential equations. So remember that this shifted convolution sum is really coming from the solution to this particular PDE. And so we might ask ourselves, okay, what if we look at the homogeneous solution to kind of a more general class of functions, EA and EB here. So what if we kind of look at more of these alpha terms and see if at least computationally they turn out to be 0. Okay, so we end up basically generating an entire family of these shifted convolution sums times some sort of like polynomial times log function. So they all have this kind of similar flavor to the to this particular 3/2 case, but just with different polynomials here and different sigma divisor functions depending on the solution. Okay, so our first example, like I said, is this one coming from the 3/2 case, and at least numerically, this thing turns out to be true. An even simpler example, you can kind of generalize, at least numerically, for these sigma 0 divisor functions, we would get some similar identity in this form, a nice cute formula, and at least numerically, this thing turns out to be true. So we ran a few more examples. And so I think this again corresponds to some 3/2 Eisenstein series with a slightly larger eigenvalue. So we have some kind of polynomial thing going on here, and we expect that it looks like some slightly different combination of zeta values. And this one we computationally checked. We basically just took this as the difference between the left and the right side on the previous slide. And we saw that like at least there's this kind of weird like periodic thing that we're off by. Like it looked good, and then it looked so much worse. And why is it looking sometimes good and sometimes bad? But mostly not that great. So Ksenia and I, we ran a bunch of these computations and we didn't know what was going on. We thought we like did something wrong with our prediction. So we sent it to Danylo Radchenko and we sent these images and he said, I know what that is. That's that ratio of L function values times the Ramanujan tau function over n cubed. Cool. So that was fun game. So he gives this ratio of L functions times, and so this is the Ramanujan tau, so that's the Fourier coefficient of the Ramanujan delta function, right? So we're basically getting some sort of like almost Fourier coefficients of delta functions, just kind of weighted by some L value. So that's our error that we're off by, right? Basically add this thing in and then you're golden. Your identity holds. So, well, that means this is not, the expected identity is not 0 or vanishing in this case, basically. And then we did it again and we said, try this one, Danylo, and he did it again. I don't know where he gets this from. No, I asked him, but it still wasn't that helpful. He was like, I was working with similar things. Sure, me too. So here, this is something for sigma 4 divisor functions. I mean, just another example. Here we're again off by some tau function, or the tau function over n, and then this L function, this ratio of L functions. And so what we end up doing is we just kind of parameterize these examples, try to come up with a family of them. And the bigger question was like, what is the generating function here, so that we can always get some sort of coefficient of a modular form. And then the other question, of course, is if we get that generating function, can I get any modular form of any weight, or am I just always getting weight 12? Well, that seems unrealistic. And so the answer is we can get any weight for a coefficient. And so what we realized was if you parameterize your basis correctly, the nice generating function for these alpha terms is in terms of actually a Jacobi function of the second kind, which somewhat makes sense as the way it's defined as some sort of solution to an ODE. So we have this, those end up being like our coefficients phi. These end up being like basically those zeta values and derivatives of zeta values that we show up as predicted. And then we said what it actually turns out is this is always equal to a Fourier coefficient of a modular form over n to the d. And I can tell you which modular form it is. So it's going to be a Cuss form of weight 2d plus R1 and R2. So notice R1 and R2 are really depending on the Eisenstein series that we started with for our differential equation. And then the d is kind of depending on that eigenvalue we had for our original PDE, that differential equation. So we get this, so this is our Cuss form of this particular weight for SL2Z. And it is weighted so that, it's normalized so that by this factor lambda f, which basically, I think this is using identities of Manin. We had like some ratio of alpha values, but using identities, I think of Manin, you can get this in terms of a product of L values. Okay, those weird, these types of coefficients that we have. Okay, so we were able to kind of conjecture what this identity should look like. And generate a Cuss form of every single weight. And we were able to prove this thing. The proof, I don't want to spend too much time on because everybody's hungry and nobody wants to hear about a proof when you're hungry. But basically, basic idea is we use the holomorphic projection lemma. So basically, we kind of rewrite, we shove this stuff back over to the left side where it belongs. And we say that thing is supposed to give you, if I multiply by ND, it's supposed to give you a modular form, right? So this is this thing summing up over exponential that's supposed to give you a modular form. And so we compute that modular form using the holomorphic projection lemma. So the idea is you want to, behind the holomorphic projection lemma is if you have a non-holomorphic modular form, you can compute the holomorphic piece using this really nice formula. So we just basically had to find the correct non-holomorphic modular form that corresponded to these coefficients. And by looking at work of Diamantis and O'Sullivan, we found this was the correct non-holomorphic modular form, this product of weighted Eisenstein series, completed weighted Eisenstein series. or normalized weighted Eisenstein series, in this case. So basically we end up just basically, that's my phi tilde. I then want to compute my phis, using this holomorphic projection lemma piece. And what I'll get out is a holomorphic modular form by like definition. And so we compute these eighths of n's corresponding to this phi tilde, and we see that they are exactly basically what we wanted as these coefficients. So let me see here. We compute each of these a's by computing the Whittaker functions associated, integrals of Whittaker functions associated with these Eisenstein series, and we get exactly the Jacobi function and those c's that we had before, as desired. So I feel like there was a point, which is, so the nice thing is, so we do have the identity we expected to hold doesn't exactly hold, but in the case that we were originally looking at, which was nicely conjectured by here, where we should have this thing is equal to 0, we still do actually get a general proof of that identity because, oops, sorry, in that case, the weight of the cos form that we would get here is weight 8, and what do you know? That's just 0. There's no cos form of weight 8. So that gives us a proof of this original identity that we did want, as well as, of course, these other examples, you know, with the error term included. Yeah, and so the questions that remain. So again, we want to find a generalized closed form for this Fourier solution. I mean, ideally not just in half integers, but that's what we're starting to work on now. So it would also be nice. We have this proof of the vanishing of in the particular case. I should have kind of reworded this statement, but so we have the proof of that the alpha n's vanish in the particular case and that they are equal to Fourier coefficients in kind of a more general setting. But it would be nice to extend something like this result for not just integer, so even integer R1 and R2. So extending this beyond even integer R1 and R2 is going to recruit stuff not just from the holomorphic spectrum. It's going to get, you know, some other pieces, and so this result would probably be very similar to earlier work of Motohashi, but it would be nice to kind of see if there's other special values that we can consider for those things there and get some other nice identities. And then of course working on higher rank solutions is something that's been ongoing by many, and so that's one area that we'd like to